Today we're going to get some live structural moments just by clicking and dragging on structures. Here I've got a veer and deal truss, and you can see the moments are developed just by clicking and dragging my mouse. And here I've got a portal frame, so it's really cool that I can get live moments just by clicking and dragging my mouse. It's a lot quicker to get a feel for how the structure might behave based on loading it in different ways. And a reminder that you can get more tutorials like this at our website, and you can also download the scripts if you prefer rather than building them yourself from the videos. And feel free to have a look at some of the other services we offer, including model conversion, reinforcement, visualisations, etc. Okay, to keep this quick, I've just drawn the curves of a veer and deal truss in Rhino, and I'm just going to inherit them into this curve component that I've named. I'm not actually a fan of the veer and deal truss. It's not very efficient because it relies on bending, which is a bit weird for a truss. And there's other problems like the connection details and how you fix it to the rest of the structure. It's a bit annoying when architects bring it up, to be honest, but that's what we have to live with sometimes. Now we're going to divide this curve up into equal segments. I'm going to set it to 4 segments for each curve. Then that just gives me the points, so I'm going to create a polyline from there, and then I'm going to explode it. It's just a quick way of creating little curved segments. There's other ways of doing this, of course, but this is pretty efficient. Now if we look what we need in Kangaroo, we're going to use this beam component. So I'll drag that in there. That uses a start frame and an end frame, apart from the beam properties, with the start and end frame being a plane rather than a point. So I need to get some planes at the start and end of each of these beam segments. So I'm going to do that with P frame, which is perp frame. And to do that, I'm going to parametrize this, and the T parameter is the point on the curve, and it's from 0 to 1, so I'm going to make that from 0. So that's the start. That's our start frame. And the end frame will be a point 1, which is the end of the curve. Now I'm actually going to leave these all set to 1 at the moment, because we're not really getting exact values out of our beam. We're just using it as a graphical tool this time. I might talk about that in a later video. So we've created our beam. Now we're going to need to have a solver in Kangaroo. I'm just going to use the standard solver here, which is the original. Now that needs some goals. A reset, it's good to have a button for that, and whether the solver is on or off. So I'm just going to set this up now. I'll have a Boolean toggle. So that just turns the solver on or off. Sometimes if you have a huge amount of data or a huge amount of points, it's good to just leave it off because it's constantly working. And I'm just going to put a button on here, which is going to reset the solver if I have any problems. It's always good to have these two. In fact, I'm just going to Control G group that, and that's our control for the solver. So with this beam component, I'm creating a goal. Other goals I'm going to need for a veer and deal truss, if it's going to be statically determinate, is some support points. Now I'm just going to turn off these planes because we don't need to see the planes. I might as well turn off all the other stuff as well, all the points, etc. So to get some support points, I want one there and there. So I'm going to go to the Kangaroo component and go for the support. I'll just find it. There it is. It is in here somewhere. Oh, there it is. It's in 6 degrees of freedom. Okay, so to create a support, I need a frame similar to the beam, which is basically a point, but in a direction. Just ignore target for the moment. These are the freedoms of the support, so X, Y, Z translation, so whether it can move in those directions, and then rotation, whether it's fixed or free, and how strong that support is. So I'm just going to set up some toggles for this, so I can set. Now I'm going to make it true, so it's fixed in X. I'm going to fix it in all of these. Fixed in X, Y, Z. I'm going to have it fixed in rotation about X. Now I'm going to actually release it in rotation about Y because we want this to start bending, and in the Y direction, which is in and out of the page, I want this free to rotate. And in the Z, I'm going to make it fixed as the other ones. Just line these up, make it a bit neater. Whoops, what have I done there? Sorry, I've moved that to strength, so I'll just undo that, disconnect that. So that's one support. I'm going to create another support for the end. Now I need a point. Which I'm going to turn into a plane for the input. So the plane's going to be in X, Y, and I've got an origin point. So if I just go and set this point here, which is 0, 0, 0, put that into frame, that's giving me one support. I'll just copy this. That's another support, but this point I'm going to set as the end point. Now I'm just going to turn this off because it's just a bit of extra stuff I don't need. Right, so we've got our beam and our two supports. Now I'm going to use a component to combine these in a certain order of data that this solver prefers. And what I'm going to use for that is intertwine. Now if you zoom into some of these components, you can expand or reduce the number of inputs. I only need 2 in this case because I'm going to put the beams, and remember there's quite a lot of beams because we split it up into 4 for each line. Put that into the top, and the bottom will be our supports. And then the last thing we need is a way to get some input from the mouse and put it into the solver. So the way they do that in Kangaroo is to use this grab component. I'll put that down there, and I'll also put that into the part with the supports. So it's best to have the beams separate from the supports and the other goals. So that gives me a 2-part entwined result, which I'm going to put into the solver. Alright, so the click and drag should already be working. I'm just going to internalize this series of lines and get rid of them out of Rhino, so they're just in Kangaroo. I'm going to turn this to true, so we've got a converged result in our solver, and you can see already that we can just drag parts of the frame and it's performing as beams that have stiffness, and they're deflecting based on a point load being moved around. Alright, so now we want to get some structural moments out of this. And there's a little bit of a trick to this. So this is where Kangaroo's maybe not quite as user-friendly as something like Karamba, for example. But what we get out of our solver is how many iterations it's taken, some vertices of the beams, and this data here. So if I have a look at that data in a panel, we can see it's this system collections generic stuff. So that's actually Rhino data. That's not data that Grasshopper can see straight away. So what I'm going to do is, firstly I'm just going to explode this tree so that I can split up I can use the first and the second branch of the tree that we created over here, because we only really want the first branch. Now the next trick, I'm not going to explain a lot of this, but because we've got system data that's in the Rhino's default language, we need to get that into Grasshopper's data format. We're just going to run a script, C# script, which is under maths. And we're going to put this first branch into X. And it's really easy. All we need to do is to say A equals X semicolon in this private void run script area. All that's saying is A is always the output, and it's just saying the output is the input. Now the reason this works is that it will convert. The C# script component will convert internal Rhino data into stuff that Grasshopper can understand. So it's a bit of a hack, but it works. You can already see the planes have shown up as an output of this result. So I'm just going to turn that preview off. Now, all I've done now is to get these streams of data. So there's 7 outputs that the solver produces. I'll put that into there. And I'm simply going to just zoom in and give myself 7 outputs, 0 to 6. So I know that from playing around with this, that the first one is a plane. So if I go to primitive, plane, the first 2 are the start and the end point planes, because it uses planes for everything. I'm just going to unpreview that and these. So that's my start and end plane, basically points effectively. But okay, and the next one are numbers, and they represent the values of the moment in the X and Y direction. So I'm going to call this MX A. And this is MXB for point B. And the next one is the moment in the Y direction. So this is going to be MYA. And this is MYB. Oops. Now the last one is torsion, which is also a good property to get out. I'm not going to use it in this tutorial, but you can think of ways of using it for sure. Just make that a bit neat. Okay, so to draw a graph of these moments, because they're just values, they're just numbers. Now I'm just going to simplify this while I'm here. So the easiest thing to do is to make some lines out of this output. So I'm just going to create a line. I'm not even using the plane data, I'm just using it as a point. Whoops. The other line. Line between 2 points. Between the start and finish point, I want a line. So now if I drag it, I've got a line joining the points. That's pretty easy. I want to make this look a little bit better, so I'm just going to use this surface pipe component. Now that's made huge pipes, but I'm going to set the radius to 0.1. That's a bit better. So now I've got points, pipes, so it's just given a 3D shape. And lastly, I just want to show this display. Give it a color. I'm just going to get a swatch. There we go. Now I'm just going to unpreview some of this stuff which we don't need anymore. I'm going to underpreview that as well. Okay, so now we can start drawing the moments, and to do that we're going to use this component which is point orientated, and we can use the information we've already got in these planes rather than just the point information, because it's got a vector in it as well. So we can draw, this allows us to draw a point in a plane, so we just have to give it how far in its internal coordinates rather than the universal X, Y, Z. So the plane's already set up for us. We just need to give it a value. And what we're going to give it is the Y values, which are, you can see the Y's are in and out of the page, but they're the moments we actually want to see in the plane of the elements. So I'm going to give that U value, which is basically the internal X of this plane, the Y moment. Okay, so it's going to be really small, so we're going to have to amplify this. And to do that, I'm just going to do a simple multiply. I'm going to take this number, I'm going to set up a slider. Make it from 1 to 10. I just know these values work. put that in there, and you'll see in a minute, but I'm going to change this to, I'm going to put a -1 in there, depending on your sign convention, which I'm not going to go into here because people have arguments about that, about whether the moment is on which side of the member. Structural engineers do it one way, other people do it another way. I'm not going to go into it right now, but suffice to say you can switch it if you prefer the other way. And the way I'm going to draw this graph is I'm going to make a surface out of 4 points, which is this component. So the first point is obviously going to be the first point in the plane. The last point is going to be the end point, point A and point B. The second point is going to be the result we've just got there. And the third point is going to be similar, but using the B moment. So I'll just control copy and paste that, and it's MYB. And that goes into X of its plane. Now I've seen an error that I've made there. This point needs to be the second point. So if I drag that now, there we've got them, the moments. And like before, I'm just going to clean it up by doing a preview of this. Turning off the stuff we don't need. There we go. So I think this is really cool and useful to get some live feedback on structures you might want to test out to see where the moments are happening, especially if you want to test quickly, you know, where point loads are going to go in some unusual positions. Anyway, let me know in the comments if you thought that was useful, and anything else you want to ask, and I'll try and answer it. Thanks for watching this structured parametrics video. Leave a like or subscribe if you found this useful, and we'll see you in the next one.